I would like to welcome Jason Kimnitz, and we'll be presenting on SDCL design examples, software, and design resources. Jason is a senior bridge engineer with Wilson & Company.
Well, thank you much. I'd like to thank Florida International University, Kathy, and Dr. Aziz for allowing us this opportunity to share our experience using SDCL here at Wilson & Company on the farm design build project. I'll be sharing my experience with SDCL on that project. A little about Wilson. We've got a fair number of offices through the country here, about 800 plus employees. So felt like we need to share a little bit about who we are, the services we provide, and the markets that we provide to. Here in our Kansas City office, where I'm located, just on the Missouri side, along with our Omaha, Nebraska office, we have about 6 bridge engineers, and we had about that many during the farm design bridge project as well. We all work pretty well together, so we were able to accomplish quite a bit, and it was a great experience tackling this project. As you can see here, the farm bridge project that we tackled, we decided to introduce the simple for dead load, continuous for live load concept for steel systems. We had the opportunity with Layman Construction, which is now Capital, they've since been acquired by Capital, to push forward with an innovative solution on the number of structures that were going to be replaced on this project. As you can see, there were 41 bridges based on the number of triangles over there on the right side map that were included in this project. Brian Hartnagel had hit on this previously. We did select 31 of those bridges, 25 of which became SDCL. So in order to introduce the SDCL concept to MoDOT within the design build project, we were asked you typically would submit an AS, an additional applicable standard. And we started that process by locating the Oregon DOT has a standard for SDCL. This is just a snippet of that standard. Their standard also includes detail for seismic as well. It's very similar to the slides you saw Dr. Aziz share. This is available on their website if you wanted to reach out, but we included this in our AAS. Had I known Ross Barron would have been so convincing with his presentation, I probably would have just had him talk to Brian, and then they would just accepted it without an AAS, to be quite honest. But as you can see here, a lot of our details did come from the Oregon DOT, and we ended up using a steel block down below, as well as a solid end plate on the girders, similar with the holes through the webs to help anchor it into the concrete diaphragm. We also show a construction joint that's about 1/3 to 2/3 the height of the girder to help stabilize those beams during the placement of the deck. So a lot of this stuff was very similar in our detailing. This is the layout of all the bridges that we did SDCL for on the farm. Over here on the right, I've shown a kind of a representation of the span arrangement along with the skews that we use, and as well the W shapes that we use, kind of give everybody an idea. We had pretty shallow girders for the project. We had pretty short spans as well. I will say on bridge 40 there, I will mention that it was on a curve and it was super elevated. And all we ultimately did was widen that bridge a little over a foot and then striped it for the curve. So we didn't have kink girders or anything like that. We didn't venture down that road, but there was an opportunity to probably do so. Instead, the contractor elected to just make it a little bit wider. So the real advantage that we found, the contractor and ourselves found here, was the time savings of not having field splice during your erection. The other advantage that we had was the span ratios for the end spans and not having uplift. You can see here I've created my general elevation shows in the hidden lines, you will see the existing substructure elements that are located very close to the proposed pile vents. And because those end spans were advantageous, those span ratios are advantageous, we were able to keep that footprint pretty tight for all these projects. And in the use of steel, we were also able to keep the grade raises to a minimum. I'm not sure if we even had any, quite honest, but they were advantageous for sure on this project. I wanted to kind of run through a timeline of the time it took the contractor to construct a bridge on this project. As I had said, we had 25 of them. All the plan details were very similar in nature, so it made plan production very efficient, design very efficient, and also made construction very efficient. So at week 1, typically, you clear and grub, pull your channel banks back, and then drive pile at your vent. This is a similar picture Brian showed here. You can see that they're driving pile there at their intermediate vent. They have formed up their end vents, and they've already driven pile at their end vents on the right side there. Week 3, they're going to place their formwork at those vents. As you can see by the green lines, and the red is what's already been placed. So as you can see on the right side, you got your end vent forming going in. On the left side, you have your form still in place for your intermediate vents. They've already placed the concrete in that picture. There's an example there. So within that same week, you are then going to place the concrete at the intermediate vents for the cap. And then you can see here that they got some strip forms over on the left, same on the right there. Pretty solid example. One of the advantages that we did use pile vents up here in the northeast and northwest part of Missouri. They have some soils that were pretty scour unfriendly, if you will. So the undevelopment links on those pile were pretty large. So we had a number of pile on this, but having a superstructure weight that was minimized by the use of steel as opposed to concrete helped with this. Week 4, we were place your bearings, and then you erect your beams, and then place your slab formwork as well. As an example of that, you can see them erecting with a rubber tired crane that's set up in one location. They were able to erect the beams probably in a long morning for the most part. So on the right side there, you can see we had some diaphragms, had some attachments, twin girders within each span. It took a little bit of time, but not too bad. Week 5, you're going to place a partial height concrete diaphragm at your vents prior to your slab concrete being placed. And this here you can see on the right is at the end vent. So we're placing that concrete diaphragm up to basically the full height of the beam at the end vents to stabilize that. And we're placing these about 12 hours prior to the deck placement. Was a note that we had on our plans, just to give the concrete a little time to solidify and provide that stability for the girders. On the left side, there's the intermediate vent. You will see there is a steel plate located there, and that's to really control the cracking that occurs during the placement of the concrete for the slab. And after that, curing in 12 hours of that partial height concrete diaphragm is located there too. So it does help control that cracking for this detail at the intermediate vent. Let's see here. So then we place our concrete in the slab. As you can see here, all the slabs were poured from one end to the other. The yellow portion there is actually the bridge approach slabs. We did have a detail that we took from Nebraska where they do a continuous pour from bridge to slab on the approaches so that they're placing everything at one time. So that cut down on the time to have to wait for things to cure and whatnot. So setting up screed and all that stuff. Once you had your slab cured out, you can then come in and place your concrete barrier. As Brian had mentioned, you did your slip forming of that 42-inch barrier, then you open it up to traffic. Here on the right side, you can see was a tractor using that. So it literally is a farm project. Now, in gathering information for SDCL before we went down this path, I really had to educate myself on what was out there, how the concept worked. There were several reference materials that I was able to locate. And in July of 2005, Ross had mentioned this is one of the studies that was done with University of Nebraska and NDOR at the time, and Dr. Aziz Amini had led that. The second reference I found was done in 2009. Once again, Dr. Aziz Amini was involved in this, and basically looked at different SKUs and connections and that kind of stuff in this study. And the fourth one, which is one that I found most helpful in the design for this concept, was this one done in 2014, where once again, not surprised, Dr. Aziz Amini was involved in. And then there was a fourth item of resource that we did locate with ABC Construction, where they speak of link slabs to be used at the intermediate vents or piers. It's not a direction that our contractor wanted to go. We weren't really looking to save that much time on this, so we opted not to use the link slabs in this, but it was nice to know that was an option. So once we had a really good understanding of how this needed to be designed, we then ventured out to try to figure out what softwares were available to help us do this design, right? Because it is SDCL, it's really pretty simple. It truly is pretty simple. You could pretty much design it using Excel or MathCAD if you chose to do so. But we did find out that we do have AASHTO-aware BRD and BRR. The states around our area do require a BRR to be run on all new bridges. That was part of this project, provide those load rating models. So we do have a license for BRD as well. And so we did find that AASHTO-aware has the capability to design these, as well as MDX software. We, in our first design, did compare the results of these two programs to make sure everything was on the up and up, as well as some hand counts to verify that as well. At the time this project was designed back in 21. So Lead Bridge Steel was kind of young time, but I have since talked with some folks within the company that uses this, and you can basically group different groups and provide SDCL capabilities as well. So I think they do have the capability to do so as well. I just haven't ventured on it. So I wanted to show you just how easy it is in MDX to design this. In your conditions, you would want to include the statement hinges for total self-weight only, along with the self-weight for dead load 1. So you want to allow it to calculate the weight internally as well. And then within the data, you would want to define your hinges. This bridge in particular was 41, 53, 41, I believe. And so you will notice there that the hinges were not located directly at the supports, but instead MDX direction was, when I reached out to support, was to actually offset those slightly. I chose to do so by a foot. So you could, I think, get 6 inches to work, but it did allow for it to work here. Oh, I'm sorry, the spans there were 30, 47, 38. There you go. So there it is. So your spans were there, but I offset those about and got it to run. In AstroWare BRR, BRD here, what you do is once you get into the member alternatives exterior or interior beam, you would then click on a box here, see in the middle right there. Let me see if I can do this pointer. So you can see right here, you have a simple for dead, continuous for live load option. So you just click that and it does allow you to design for SDCL. I did include a couple of moment diagrams. On the top one is the moment diagram for bridge using SDCL. And as you can see, I know the colors are probably tough for everybody. We got dead load for the beam and here, and then here's for the concrete of the slab. And then I just use lane load and they show you positive and negative. So you can see the live load, both in green and purple, are relatively the same between the traditional continuous for both dead and live and the both simple for dead, continuous for live option. You can see the difference obviously really lies with the dead load, as expect, as you have zero moment going across that support. So you can see the difference that really kind of plays with, if you just kind of compare the deck load moments, how much that you're looking at 230, 240 kit feet for the simple situation on midspan, and then transferring basically becomes a negative moment, transfers over that way. So it's a pretty neat system. It's just got to size your beams a little bit different, but you can see how that load really transfers based on the concept here. So what I wanted to mention on this farm design build project, there really was nothing exciting about the materials. It's all pretty traditional stuff. We use 4,000 PSI concrete, as you would typically, 3,000 in the substructure, used 50,000 PSI steel for the beams, depending on whether or not it was over water or whatnot, whether it was specified weathering or it to be painted. Just determined that. But as mentioned previously, and Gary will get into that a little bit more, is we ended up coating everything. So there was no painting necessary or weathering steel required. So to get the nuts and bolts of things here, this is really pretty simple on how you design this. Dr. Z shared this equation earlier, and what you're doing here is to calculate the capacity of your connection is truly just the moment arm, your steel and your deck. So based on the centroid of your steel block below you come up with. So it's kind of an iterative process between determining how much steel you need in your deck compared to the size of the block that you're placing at the compression flange at your intermediate support. So when you rearrange that equation, you can solve for the area still needed. And then as you can see here, there's also an equation for the minimum height of steel compression block. And then in order to ensure that the bottom compression block remains elastic when the ultimate capacity of the connection is reached, the required minimum height of the steel block can be found using this equation, assuming like the ultimate strength of the tension reinforcement. And based on the results, the research that was done in the study I found, the ultimate strength is assumed to be at 1.7 times that yielding strength, which explains the 1.7 there. So in using these two equations together, we came up with a spreadsheet here. And what typically you would see traditionally from DOTs, your bar patterns are either a 5-inch spacing or 6-inch spacing. Out midspan, you're 15 or 18 or something like that, right? So what we do, like you would do with any pre-stressed concrete structure, you're going to put bars in over that support for continuity for the live load scenario. So what we did was we were able to determine based on the bars area for the continuous bars at 15 or 18-inch spacing, what the capacity was at that section. And then if we added 1 bar, what that capacity would be, and so forth, so on, 2 bars, right? So as you can see, we then took results out of AstroWare, placed them in the spreadsheet. We then looked to see for a strength check where we would then need to add additional bars, right? So as you can see, what we were able to do, our maximum moment was 712. Adding one bar was 909. So we knew one bar would be sufficient. And so that's how we went about doing that for all these bridges. Again, with this equation here, we were able to determine the height of the minimum height of the block needed based on the area of steel. So you can see this 857 is what we plugged in there, pulls off from the top there, takes the width of your flange and determines what the minimum height of that block would need to be. Now going back to the spreadsheet here, you can see we have a little note here. So we ultimately ended up using blocks that were square in nature, I guess. So we used a 3x3 block. And the reason we were a little conservative on the size of that block, because your construction tolerances, you can be a 1/4 inch off on bearing seats. You can potentially, your beam heights from one span to the other is a little bit different. So that contact height may not truly be the full 3 if we specified a 3-inch block, right? So when we were calculating the height of the minimum block of being 1.6, we wanted to give ourselves, our contractor, a little push to make sure that we could make that happen in the field. And so that was a good detail for them to make things pretty simple. And to kind of reiterate, the whole reason for the block itself and the compression block, when you're sizing that, you want to make sure that you size that so that it's not too small and that it wants to fail prior to your deck steel. Okay, you want to be able to see the failure occurring in your deck when you're doing an inspection, biennial inspection, and making sure that if there is a failure, that you're seeing it on the deck as opposed to inside the concrete diaphragm, which you'll never see unless, I don't know what would happen there, I guess. Catastrophic failure, possibly, I don't know. But here's a detail of the slab bars that we had on this project. As you can see, we had 14 number 5s that were continuous, and then in between those, we slapped in some number 6s to make that continuity across the piers. This is just kind of a additional detail of our typical detail for the slab. As Brian had mentioned, we were using 7'2" girder spacing and 2'7" overhangs on this, and we did that for every one of them. Everything was an 8.5-inch full depth deck. If our contractor would have chose to use precast concrete stay in place form, that might have been a little bit more difficult to use SDCL. So we are glad that we did do the full depth on these, and I think that it did help win the project, because with the full depth slab, it was a little more healthy long term, I guess, for the structure itself. This is a typical detail of at the intermediate bent for the concrete pile cap. You see here that their detail, they have joint filler around the edges. They have shear keys here to transmit the shear. And the reason for the joint filler around the edges is because they're on neoprene bearing pads. It allows it to pivot. No moment goes through this detail, just the shear gets transferred. Here's the detail that we showed. Basically, you can see that we called out, I don't know, some of these beams were pretty shallow in nature. We had 12 inches all the way to 24 inches. So some of these 12-inch plates, it basically became bars as opposed to a sheet metal gauge. But because we also had these dowels that were placed in there for shear transfer, we had to orientate them in an X-vert pattern so that we could slip that plate in between there to control that cracking during the placement. There really wasn't anything fancy about the rebar in the concrete diaphragms at the intermediate supports. This is a pretty traditional detail for MoDOT, which really was in line with what the Oregon DOT showed. So we really didn't modify anything with that steel there. As you can see, this is a detail of the end plate and the compression block that we chose to do. As mentioned previously, Dr. Aziz said, they talked about using a connection plate on the top and do a bolting, but then we kind of felt that defeated the purpose of getting rid of the field splices altogether. Why get the bolts out at all? So, and the wrenches, right? So we opted not to do that. We went with the full end plate as opposed to not having a partial height or something like that. It just increases the size of that compression block and really helps anchor that beam in as well. And then there's our typical 3x3 bar. You can see that how these bars are a little bit different in length. So not only are the heights different, but the widths are a little bit different between the rolls as well. I don't know if we always, I think we always used the same roll size between spans. So we never did venture down, let's go with a 3-inch shorter beam height for the end spans. We never did venture down that route. This is our weld detail for those plates. We just welded all the way up and down and along the flange, the typical fillet weld for both and then we just did a tack weld here at the block just to kind of hold it in place. There wasn't some sort of extra block the contractor had to grab and throw on. So, and as mentioned before, they would put rebar. We do put the rebar through the girders to help anchor that in the concrete diaphragm, as you can see here. This is your typical detail. You saw the one on the right before. Brian had shared that. That was one with the skew. You can see those girders were pretty well the same width and height throughout there. You can see how the contractor laid these dowels, kind of have an X pattern. And what I believe the contractor did was prior to, I think once they laid the steel on the left, which are these upside down hat bars, if you will, they would then insert their steel plate, which then also went through the girders themselves, right? So in between the girders themselves. So that was one long plate across the entire width of the concrete diaphragm. Here on the left side, you can see we had a pretty significant change in width between inspan and midspan, but yet again, that didn't change the size. We didn't change the width of the block to accommodate, to make sure they were both the same on each side. We just went full width on all of them just to simplify that detail. So with that, that's everything I have, and I entertain any questions anybody might have. I'm sure I left a little extra time, so.
Okay, Jason, this is Paul. We do have a few questions. First one I'm going to ask, these came in a little bit beforehand. Are there any existing state DOTs with this design construction method already included in their state design standard?
The one I shared was Oregon DOT, so they have that one. That's the kind of what we based our project off of. We weren't able to locate any others. I think Dr. Zeese also mentioned a few in his presentation. I do know Brian, and I don't know if I'm going to steal any of his thunder, but they are in the works of putting together some for MoDOT. So I know that's being done currently. I don't know when to expect that. So we should be able to all cheat off of those standards and do a nationwide SDCL based off MoDOT details. So.
Okay. Question came in beforehand about today's training is about steel girder systems. Does a similar system exist for pre-stressed girders, concrete girders?
Yeah, I would say it's the same system. It's what pre-stress has been using for years. It's just kind of mind-blowing that we haven't been using it for steel more so. So it's really the same concept. I mean, if you look at the detail for concrete diaphragm for pre-stress to one that we're using for steel, or the difference might be on a pre-stress, you don't have those end plates, right? Well, typically on pre-stress, you have much more end area to transverse that stress in a compression block. So yeah, it's pretty much the same concept.
Okay. The next one I have here is question came in beforehand is, can you share details of a partial end plate? You had it on your sheet 40. Is that pretty well that, or do you want to add anything to the question?
Well, I have the well details on 40. Here's the plate. The end plate itself is really just that. You can see the size of this end plate. So I'm guessing this is a W18 of some sort, right? So that end plate was truly the width of that rolled shape and the height of that rolled shape. There's really nothing too special about it other than it encompassing the full height and width of those beams.
Okay, and then on your next sheet, I think you showed the wells. Is that right? Sheet 40?
Yeah, and then we ended up welding full height in both along the flange as well.
Okay, that's fine. We had a question that came in during your presentation. Was, could you share analysis options for SDCL and BRDR?
Well,
you gave a pretty good detail in there. So
yeah, outside of what we did internally with these two spreadsheets, I know I'm probably clicking a little faster than what my speaking's showing here, but using the software themselves, you kind of have to get in and do it. It's really pretty simple. It really doesn't add a lot to what you would already be familiar with both these softwares. So if you use either of these softwares traditionally to do design, it's not much different. It's just some key factors. So could I provide an example? Probably at a good price I could, but
oh, that's good. We have a couple more here. Have you had an opportunity to design a bridge using SDCL steel systems since the farm design build project came about?
We have not actually. We've done those are the only SDCLs we tackled at that time and since. We've had opportunities presented to us to maybe provide an alternative to what was submitted during design during letting, but those never came to fruition either. But I think a lot of that has to do with the fact that I'm seeing a lot more of those in the state. I've been in Missouri, and so I think a lot of people will recognize that SDCL is a pretty advantageous system to be used in the right locations. So.
Okay. The next question we have here is, what is the biggest advantage you feel the SDCL steel system has to offer?
Well, I think erection for the beams themselves. I think Gary will get into this a little bit, but the time it takes them to do this, to erect those beams and then get deck on the forms up And it's, as you can see, they're tackling these bridges in about a month and a half, 2 months time, which is really pretty quick. Box culvert would take about a solid month. And then if you go next to SDCL, you're looking at maybe 2 months. The traditional, you're looking at maybe 3 months, minimum, right? So I think it's the cost savings on the ground for everybody all around, really. And then as far as the designing it, it is pretty simple. So design-wise, it's advantageous to tackle it. It's not more time-consuming than a traditional structure, I guess I would say.
We did have a question come in from the audience regarding temperature gradients and whether or not those are considered in the design.
So we had temperature loading, obviously, on the piers as supports for your pile at the vents there. So as far as when you're erecting the steel, if you think about it, you're erecting the steel in a week's time and you're putting the deck on it within 2 weeks, right? So how much temperature can really fluctuate within that time span is pretty minimal. And what Dr. Aziz had alluded to during his presentation was that the contact of those two compression blocks between the beams didn't need to be 100%. You could have a 1/4 inch gap. It fills with a little bit of that concrete cream or whatever, a little bit of that concrete paste, or we'll get in there and fill that up, and it still works just as designed. So
okay. Next question is, what is the live load deflection for this structure?
The live load deflection criteria, it would be the same as any other. I think it was LR 800. We made sure that we met that. We didn't have any sidewalks on these, so we had to hit LR 1000. With those 12-inch beams, it got to be pretty close. So as you can imagine, but yeah, we just use the LR 800.
Okay. You mentioned bearings. What type of bearings were used?
So MoDOT typically will do a plane pad. So there's a little 1/2 inch plane pad underneath at the end vents. At the intermediate vents, because it is allowed to rotate, they will use a reinforced elastomeric bearing pad. Depending on whether or not the slope is significant, they would also maybe taper that shim plate. It's the shim that's inside the elastomeric. But yeah, it's really 5/8 inch thick at the intermediate supports and 1/2 inch at the end vents. So it all gets encased when it's all said and done.
Still have a few more minutes. How have the galvanized piles performed in the long term?
I know that I probably can't speak to that wholeheartedly. Brian probably have a better idea. I was the district bridge engineer for MoDOT for 1 year in Kansas City, so I do know that you do have scour at your end vents. Either it be a stream crossing or really a grade separation where you have bad runoff details or something that's coming around your abutment wings or something, right? Or truly under the roadway. It can sneak up underneath there. So then you have issues with drainage. So having those galvanized really is advantageous at that ground line for any water erosion that might occur, and really helps in controlling any deterioration that may occur, and any difficult details you might have to come back and have your maintenance crews tackle at a later date.
One last question. On the farm projects, was the bridge length equal to the bank full width over the water?
I think our footprint for most of our bridges were slightly larger than the existing. So we were able to go, I believe it's 3 feet, no closer than 3 foot to any existing timber pile, is what we did there. And so our bridges were a little bit larger. Now, some of the older bridges, they had depending on their wing detail and what their existing slopes were, because we weren't really touching much of the bank anyway, we were able to utilize what was there as stable, and then really only modified anything based on any rock length that was needed, or really close to the invent itself for that 2-to-1.
Okay, that sounds great. Well, thank you very much, Jason.